Okay. I was just picking my writing pen because sometimes the pointer is just too tiny, and I feel that it helps. Okay, now we are looking at degenerate systems, right? To look at the exam question you sent to me, I decided to bring an example that is going to help us to understand that better. Right, determine whether the system has no solution, infinitely many solutions. If it has no solution, explain why. Else, solve y of t in terms of x of t, where x of t is an arbitrary function of t. Right, how do we start? To start with this, we say in operator. We actually say in operator notation. In operator notation. Right. Um, in operator notation, the system becomes right. So we need to write the system in operator notation because sometimes they use the dot, the x dot notation, so we can transform that into the operator notation. So in the operator notation, this becomes precisely d plus 1 into x. And then we have minus into d plus 1 into y. And this is actually equal to e to the e out of 2. Right, obviously this one here becomes twice d minus 1 into x minus twice d minus 1 into y. Okay, into y. All right, into y, and this is equal to 5 e to the minus t. Okay, so we've written this in operator notation. Right, having written it in operator notation, it can be transformed into the determinant expression. Hence, we have d plus 1 minus into d plus 1 to d minus 1 minus into 2d minus 1. Right, so we actually obtain the determinant of this, and the determinant of this can be seen as d plus 1. This goes with that. Minus into twice d minus 1. Then we have a plus d plus 1 into 2d minus 1. Right. Minus into, this is 2d squared. Right. Minus, figure it out, 2d squared minus d. Yeah, minus d and 2d will give us like a 3d. Minus d and 2d will give us a d. And this would give us a minus 1. And this can multiply straight away. This is actually 2d squared. This is minus d plus 2d. A d minus 1. What is this? This is 2d squared cancels out. Just the minus d cancels out. The 1 cancels out, giving us a 0. Okay, and this observation makes us to infer that so that the system, is degenerate. It is degenerate. Right, the system is degenerate. The conclusion of degeneracy arises from the fact that the determinant of the coefficient matrix here becomes 0. Next, we use the notions we know from Cramer's rule. Furthermore, since we have the determinant of the, so in view of the notion of Cramer's rule, so we take the first column and we replace the second one by these functions. So we'd write d plus 1 to d minus 1. Right, we'll write d plus 1, we'll write 2d minus 1. Those functions are e to the t out of 2 together with 5e to the minus t. Okay, I mean, in this case, because the system obviously is degenerate, these becomes equal to, even if you take these functions, you put them here, and you have the 5e to the minus t, then you take the second column of that matrix, which is formed by this here, minus into d plus 1, minus into, yeah, the minus into d plus 1, minus into 2d minus 1. Okay, they'll be equal to each other. Let's see what one of them equals. Let's just work this one out. We could work this one out. But in this case, because the system is degenerate, it is expected that they must be equal to each other and equal to 0. Okay, so this with this, it becomes minus twice d minus 1 e to the t over 2 plus d plus 1, 5e to the minus t. And therefore, if you differentiate this one with respect to t, so it's going to be minus, the derivative of this is only derivative of the top, which is 1/2 with respect to t. But there's a 2, then you have e to the t over 2, then you have plus e to the t over 2, then you have minus 5 e to the minus t. If you differentiate this one with respect to t, you only differentiate the top, which is the derivative of the t is minus 1. So that's what we get. And then this one by 1 is exactly the same thing, like that. Okay, so we just remove the brackets here. It gets in e to the t out of 2 plus e to the t out of 2 minus 5e to the minus t plus 5e to the minus t, and the result here is 0. Okay, now the result is 0 makes us to infer that thus the system has infinitely many solutions. Okay. Because this system has infinitely many solutions, so what do? We let x sort of the first variable because we have x
Hello?
and y. Yes, please.
Can we go back?
Okay.
What happened to D here?
Okay, what happened to that one? All right, obviously at this point, 2 cancelled 2 in the half. When 2 cancelled 2, then we had minus e to the t over 2 plus the e to the Okay, yeah, because at this point, if you differentiate this one, let's differentiate. So in other words, we open the brackets in the following manner. We have twice d minus 1 e to the t over 2. Okay, if you open up the brackets, first you can even allow the minus to go through, and then we have that. Okay, in a step-by-step fashion. I allow the minus to go through, then now we sort of let this operator operate on this exponential expression. So we get exactly this one here. And then now, what is the derivative of this with respect to t of the e? Okay, in mathematics, the derivative of the e, we always differentiate the top with respect to t. So this capital D is the derivative with respect to t, and the derivative of the t is 1. So if you differentiate the top, would get 1/2 plus e to the t out of 2. Okay, which is exactly this, the minus half e to the t over 2. Then obviously at this point now, if you differentiate this one with respect to t, allowing these to sort of um, come into the brackets, but also the d to operate on the exponential expression, then you have the derivative of the top of the minus t, which becomes minus 1, times the 5 here, which becomes minus e to the minus t. And then obviously we have the number 1 multiplied by the, so it remains the same. Okay, obviously we differentiated the t over 2 with respect to t, because this d, what is this d? This d can be seen as dt. That's what this capital D is. So if it is a derivative with respect to t, then obviously the 2 cancels. And we just have the minus e to the t over 2 plus e to the t over 2 minus that. And then these 2 guys cancel, and these 5s cancel out, and we left with the 0. And obviously the observation is that now the system has infinitely many solutions. From the notion of Cramer's rule, we get the solutions from these. What does Cramer's rule say, and how do we get solutions from Cramer's rule? Okay, I'm going to recap on Cramer's rule that is done in linear algebra and how we get solutions from these. Because if ever this happens, then it means that we have infinitely many solutions. But also, the fact that the coefficient matrix has 0 determinant, it means that the system itself is degenerate. And the degeneracy means that it does not have a unique solution. So if it doesn't have a unique solution, what does it mean? What kinds of solutions can exist? If the solution is not unique, like they said here, if there's no solution or infinitely many. So if it's degenerate, it means that either it has no solution or it is infinitely many. So that's the degeneracy. There are 2 cases, no solution or infinitely many. But here we have infinitely many solutions, because this is 0. Okay. Now, since this actually is 0 and therefore we have infinitely many solutions, then this is what we do if we have infinitely many solutions. We let x be another function g of t, where g of t is an arbitrary function. So g of t becomes an arbitrary function. Okay. Um, recall that. Would recap with the original things that we had this. I'm just going to write this. We wrote it in operator notation in the beginning. And then we had also minus into d plus 1. Y. E to the t out of 2. And then we have 2d minus 1. D. which means 2d minus 1. We have e to the minus t. Okay, we call this one equation 1. And we call this one equation 2. Right, then from these two equations, 2 times equation 1 minus equation 2. Okay, 2 times equation 1 minus equation 2, what is it going to produce? So that's going to produce, okay, you can easily see that. 2 times 1 is twice d plus 2 x minus multiplying by 2 is 2d plus 2y. 2e to the t over 2. This one times x. 2d minus 1y. Ah, okay. 5 here. And 5e to the minus t. Obviously, this one is still equation 2, but this one has been transformed, and we can give it the name 3. So that at this point, if you have equation 3 minus 2, okay, 2d minus 2d becomes 0, and then we have 2x minus into minus this, which becomes only 3x. And then here 2d minus 2d becomes 0, and then we have 2. Okay, this is going to be minus 2. This is going to be minus 2. And then this one is going to be plus 1. So minus 2 minus 1, so it's minus 3. Minus 3y, which is 2e to the t over 2 minus 5e to the minus t. Right. Remember that x of t is g of t, because this has infinitely many solutions, and therefore the answer is in terms of an arbitrary function where x of t is g. So wherever there is x, we're going to put g minus 3y 2e to the t over 2 minus 5e to the minus t. Okay, so now we make y the subject here. So which means that we can write 3y. We can write 3y is equal to, okay, if you move the 3y to the other side, to the right-hand side, and then we have 3g of t minus 2e to the t over 2 plus 5e to the minus t. We divide to, okay, the 3 has been moved to the right, and these ones have been moved to the left. So we have these signs. All right, and then we can divide through by 3, or multiply both sides by 1/3, getting g of t minus 2/3. E to the minus t. Okay, so this becomes therefore, because if you remember, the question was that if it has no solution, explain why. Else y of t in terms of x of t, where x of t is an arbitrary function. Which is what we did. Y of t is in terms of x of t, where x of t is an arbitrary function because of infinitely many solutions. Yeah. Okay. So we are done there.
How did you get that?
Okay, that's a good. How did we get this? Okay. Here we said that equation 3 minus equation 2. So we said 2d minus 2d. 2d minus 2d is 0. And then we have 2x minus this. So 2x minus into minus x. So it's like 2x plus x. 2x plus x is 3x. And then here we actually had this here, 2d and minus 2d, right? So obviously at this point they have the same sign, okay? So this is minus 2d if you distribute, and minus 2d if you subtract, minus 2d minus into minus 2d, the 2d's disappear, and therefore we're left with now distributing, we have minus 2y, and here we have a y. We have minus 2y and we have a y. So if you subtract these, then you have minus 2y minus y, which is minus 3y. Okay, and then we just subtract the 3 minus 2. So the d's were completely eliminated by this operation. Why are the d's totally eliminated in this problem? It's because this particular problem has infinitely many solutions. When does a problem in mathematics, a linear system, when does a linear system have infinitely many solutions? It's when one equation is a multiple of the other, and that is the sort of problem here. The situation is that one equation is a multiple of the other. 2 is the multiple of, is actually a multiple of 1, and 1 is a multiple of 2. So in that event, we have always infinitely many solutions in mathematics. Okay, I'm sure that this is a very useful one, but I did this because now it is very important for us to do the exam question of the January 2023 you sent to me. Okay, you sent me this question just a couple of minutes ago, and I was looking at the question, and hence it was well supplemented and well complemented by the example I had included. I included that example today earlier, even before you sent the question, because I just decided to look at an example on a system that does not have a unique solution, because in our previous discussion we looked at the unique solution problem. But now this came in January 2023, and let's look at how this question can be solved. It's the same as what we just did now. Determine whether the system is degenerate. So the degeneracy, we just need to compute the determinant of the coefficient matrix. In the degenerate case, decided whether it has, okay, so I read this and it was like, decide whether it has no solution or infinitely many solutions. So if it is degenerate, either no solution exists or there are infinitely many solutions that exist. If it has no solution, explain why, else find the general form of the solutions like we did. We found y in terms of x of t, where x of t was an arbitrary function. We do the same here in the January 2023 question that came. Hence, this one is already in operator notation. So what are we supposed to do? We're just supposed to take the operators, d minus 1, d plus 2. D minus 1, d plus 2. Which is equal to. Okay, so to find the determinant of this, of the coefficient matrix, we want to decide whether it is degenerate or not. So we actually sort of obtain the determinant like this. Okay, how do we find the determinant and what method do we use to complete the determinant? We use a method called cofactor expansion. We use cofactor expansion. So now at this point, we have d and d, which is d squared, plus twice d, minus 2, minus d squared, this and this. So this is minus d, which becomes a plus d with the negative outside. Twice d becomes a minus twice d with the negative outside, and we have a plus 2. So d squared and d squared cancel out. 2d minus 2d and d, and everything becomes 0. In the exam question of January 2023. So that the system is degenerate. Now, because it is degenerate, we need to know whether it has infinitely many solutions or not. Because if it's degenerate, it might have no solution. So let's look at the next investigation of this problem. Furthermore, right. Right. Furthermore, we do what we did. What did we do? We're gonna take the d minus 1 d plus 2 and then replace the second column by this and vice versa. So d minus 1 d plus 2. Okay, this is just Cramer's rule. And then now the column of the right hand side expressions, e to the minus 2t, e to the t. Okay, so we expect this one to be actually equal to when we take these right hand sides and we put them here. Now the other column is this one, d minus 1, d plus 2. D plus 2, excuse me. D plus 2. So, okay, let's just compute this one. I expect it to be 0. We can compute either this one or that one. So we'll just compute the one we have on the further right. This one, so e to the minus 2 minus d minus 1, e to the t. Okay, allow this to distribute. Minus 2e to the minus 2t plus 2e to the minus 2t minus e to the t plus e to the t. Okay, the derivative of this e, it remains the same. Now negative by negative is plus, so that we have e to the t. But obviously this e to the minus 2t, if you differentiate this one with respect to t, we're differentiating only minus 2t because that is the property of the exponential function. The derivative of minus 2t becomes minus 2, which you put before the e, and then 2 times this becomes exactly that. Now this here becomes 0, and these cancel out, and this is 0. And the conclusion out of this is thus the system, right? Thus the system has infinitely many solutions. Infinitely many solutions. Okay. If it has infinitely many solutions, what do? We let x of t be g of t, where g of t is an arbitrary function. Okay. Recall that. Okay. I'm bringing forth the questions that came in the exam. Exactly this. I'm going to write this system on the other side so that we can find the answer to the problem. So this becomes d minus 1 according to the question from the January exam paper, d minus 1. And then we have y here, which is e to the minus 2t, t plus 2, x here, d plus 2, y, e to the t. Okay, so we have this. Now, to find a solution like we did before, In this case, you don't even need to multiply because we're to multiply by 2 because the d's were multiplied by 2 in one of the equations. But at this point, the coefficients of the operator d in each case is 1. So we can call this one equation 1 and call this one equation 2. All right, and then we can say equation 1 minus equation 2 minus equation 1. Right, so if you say 2 minus 1, 1 minus 2, doesn't matter. Right, so d minus d becomes 0 if we say 2 minus 1. So d minus d is 0, and then it comes 2 minus this. 2 minus this, it's 2 minus into minus 1. So that becomes like a 3x. And then now 2 minus 1, d minus d is 0. 2 minus into minus that, it becomes 3. Then y. This minus this, it becomes e to the t minus e to the minus 2t. We want to solve for y, like we did before. So we're going to move the x to the right-hand side, making it to attain a negative in front. Like this. Divide 3 through by the number 3 and you get y of t minus x of t plus 1 over 3 e to the t minus e to the minus 2t.
Hello?
Yes, please.
Why do you say equation 2 minus equation 1 instead of equation 1 minus equation 2?
Okay, that's fine. That's a good question. I would have said equation 1 minus equation 2 is the same thing. Yeah, the answer would be the same. But just that the two would differ by minus, but can be eliminated. For instance, let's just say I'm going to write, I'm going to sort of insert it here. If we could say equation, let me write it here. Right, 1 minus 2. What would 1 minus 2 become? Okay, so 1 minus 2 would become 1 minus 2. So d minus d, 0. Minus x minus 2x is going to be minus 3x. D minus d, 0. 1 minus 2. So that's equation 1 minus equation 2. Minus y minus 2y is minus 3y. So e to the minus 2t, e to the t. What is the difference between these two equations? Okay, they differ by minus. But now if you multiply this one by negative on the left, okay, it's an optional step, but I want to solve for y, but I want to show the equivalent. You multiply the left by negative and also the right by a negative. So e to the minus 2t minus e to the t. What will this one be? So that's going to be like a 3x. Right, so that's going to be clear 3x together with a 3y, which is the same as. Now you multiply out the negative times the negative becomes a plus minus e to the minus 2t. So obviously at this point, we can see that this equation is exactly equivalent to that one. Okay, so yeah, it is the equivalent, so it doesn't matter which one you always subtract from. Okay, now with that said, we remember that x of t is g of t, so that this one becomes g of t plus 1/3. E to the t minus e to the minus 2t. Like this. And therefore, this becomes the solution to the problem. This becomes the solution to the problem. Next question. Okay, there's another question that says we need to perform a reduction. We need to perform a reduction. Reduce this system to an equivalent triangular system of the form that one. Let's perform the reduction here. See how we perform the reduction. Right. To reduce the system, we did triangular systems, but let's practice with this one. 20 marks out of 100. This paper is normally 3 hours, so it's longer. It has more time than any of the math papers ever written. So yeah, you really can relax a little bit and sit back. But this one is rich in marks. How do we solve this question? All right, and this question is very straightforward. It's something we did before. And now let's just get to do this question here and make sure that we can do it with ease. We can do it with ease. Right, we're back. You look at it very, very carefully. Right, so now what we can do at this point, this has already been written in operator notation. Okay. Now, this being written in operator notation means we need to do a couple of things. What do we need to do here to get the answer? We need to determine the solution. Very long problem. So I'm going to do it on the next page. Okay, on the next page, what am I going to write? I'm just going to write exactly these. D squared plus 1, D minus 1, the 9, everything. And then we start reducing it to a triangular system of the form that. So I'm going to write D squared plus 1 x then plus 4 into D minus 1 y 4e to the t D minus 1 x plus D plus 9 y. And this is equal to 0. We need to convert it to a triangular system. Now to convert it to a triangular system, let's just call this one equation 1 and let's just call this one equation 2. Sometimes it helps to just draw a line here than to write too many words, like do this, do that, and you can speak in symbols. Right, at this point, we can see that we want to eliminate x totally in one of the equations because they're in terms of x and y. We want to eliminate x totally in one of the equations. And to do that, we can just say equation 1 minus d times equation 2. So we can say equation 1 minus d times equation 2. So what is this? Equation 1 has d squared plus 1 minus d times equation 2. Okay, multiply by d. So you have this. So you have equation 1 minus d times equation 2. So it is exactly 4 into d minus 1 minus d times this is d plus 9. then you put a y here. So it's equation 1, which is 4e to the t minus d into the 0, d of 0. Okay, because if you say d of 2, then you must take d both sides of the equation so that the equation remains stable. What is this? Let's simplify this. So this one is d squared minus d squared, 0. And then we have 1 plus d. We have 1 plus d, which is actually d
Hello?
plus 1. Yes, please.
Why do you choose to multiply it by d?
I choose to multiply by d because I want to just remove, we want to remove x. So for us to remove x, we can just make this d a d squared. First step, we can make this d a d squared. If we make it a d squared, then it's going to remove the higher power of the d. That is we want to remove this d squared. That is the objective. So the question becomes how to remove this d squared. So we need to focus on the x terms and remove this d squared. How to remove it? We can only do that by making this one a d squared. But it's not the only way. I was looking at the question. Another way to do this would be we can multiply this one by d plus 1 because the difference of two squares this. So that would be another way to do the question. Yeah, but yeah, this one is also one of the methods that works. Okay. Right, so if we multiply like this, multiply equation 2 by d so that we can remove the d squared. Indeed, d squared is able to go away because we have d squared minus d squared, which becomes 0. And now, what do we get? So then we have d squared minus d squared, which is 0, and then we have the d plus 1. So this becomes d plus 1 into x. And then now we have plus here. Then we have 4d. 4d minus d squared minus 9d. Okay, so there's a minus d squared. So what we're getting is we're getting a minus d squared, but also there is a 4d minus 9d, which is minus 5d. Right, so you have a minus 4. A minus 4 that's going to come out of that, which is 4e to the t. Which means we have a d plus 1 x. Okay, so we have a d plus 1 x. Then we have a minus. Okay, then you have the d squared plus 5d plus 4, which is 4e to the t. All right. That's what we get. Okay. This is what we have. Right after we got these here, we can still write equation 2 below this. Equation 2 is d minus 1 into x. And then we have d plus 9 y. And this equals 0. Now, what is the meaning of all these? like we do the triangular system, to substitute once we get an equation that's sort of simpler, we substitute into one of the other equations. Normally, we substitute into one of them, maybe the first. But at this point, we are not done yet because we just have achieved these. This we have transformed into this, the original system. We have transformed the original system into this. So, okay, that is the first one. It's exactly this. The second equation, excuse, yeah, is
Can you
this one
explain
that was given? Yes. Okay. You are asking where the d plus 9 is coming from?
yeah, yes.
Okay. Yeah, you might be breaking up. I know the network sometimes is not the best.
How did
Okay.
you get the D+9? Hello?
Yes. How did you get the d plus 9, right? The d plus 9, d
And
minus
what
1
happened to
x,
the
the d plus 9 equals 0, right? It is from here. It's given in the question. D minus 1 into x, d plus 9. So it's equation 2. Okay, so we just wrote equation 2 again. But now we've been able to transform the system into these through the simultaneous equation sort of approach. Okay, we are still far from, because this is still the equation 2 that came from the exam question. But now we need to work more because we still do not have x alone. But at least now these x have d's, so we can just subtract the two equations now. So we can call this one equation 3, and this is still 2. We're going to call this one equation 3, and this one is still equation 2. Okay, what have we been able to achieve? The problem in the beginning was, in the exam question, one, the x terms, we had to remove the x and be left with only y, but we had a d squared and a d, and we had to make them equal to each other. Have we succeeded? Yes. Both the d's associated with x are now of degree 1. But now what we need to do is to remove. We need to actually remove the d now. So we're going to say equation 3 minus equation 2. Right, so equation 3 minus equation 2, it's going to be like d minus d is 0. Then this minus that. Okay, x minus into minus x is going to be twice x. And then we have this minus that. Okay, so this minus that is going to be, you can write this one as it is. Like, it's d squared plus 5d plus 4. Then minus d minus 9d. This minus that, which is 4e to the t. So this is 2x minus. So this is exactly d squared. Okay. And therefore this one is 5d minus d, which is okay, you need to check this here. Let me see. If you subtract these two, Okay, subtracted these two. Okay, yeah. Okay, this is minus, so you're saying 3 minus 2. Yeah, so this one is going to be, yeah, because this one already is a minus. And then now, this one, now you're going to have d plus 9. Okay, so that 5d plus d becomes like a 6d, becomes like a 6d. 9 and 4 becomes 13. Okay, this normally involves a lot of equations. So there's always a chance of human error because we're saying this minus that. So these two will both have a minus, which you can factor out. And then you factor out the minus, then you're just adding everything here. You're adding this one together with this. Okay, for this part. And then now you have this minus that. And then let's write this equation on the next page as it is, twice x. We have twice x minus into d squared plus 6d plus 13. D squared plus 6d plus 13 into y, which equals 4e to the t. Let's make x a subject of the equation. Making x a subject of the equation means x of t is equal to, okay, obviously you move this to the other side and then you divide 4 by 2, 2e to the t. Okay, so that in the end, then you have plus 1/2 d squared plus 6d plus 13. Okay, just like so. Let me see. Let me check. Checking carefully. Uh-huh. What is this? It is that. Okay, I'm just checking my signs, please. Make sure I'm making no mistake here. Uh-huh. So this is fine. This is fine. And then here you have this. So you have this one minus d. And then this one is minus 13. And then this one is plus 60. Plus 60. Plus 60 is correct. Okay, yeah, I'm just assessing. Please just a minute. I need to make sure that I write correct things here because sometimes the mistakes just crop up. So we must avoid them. Okay, this is plus 60 is correct. Okay. Now, this is what we have. So now, substitute into equation 2. What is equation 2? It's this one given d minus 1 into x, d plus 9 into x. So d minus 1 into x plus d plus 9 into y. So which means that you have d minus 1. The x, you substitute, what is the x? So the x is 2e to the t plus 1/2 d squared plus 6d plus 13. D plus 9 y equals 0. This is equation 2. We substitute into it, and we get this. The triangular system, the triangular system is therefore given by okay. Let's see what we are getting here. Now we have y here and y there, so we can take out y. And then if you take out y, then what do we get? Right. What do we get? Right, so let's analyze this very carefully. We need to write it properly, this equation. And how do we write it properly? The d minus 1 multiplies out, and the y is a common factor. So if the y is a common factor, we have this one is going to come and act on this one, operate on this. So if this comes and operates on that, what do we then get? Here we get 2e to the t. This does not change. So would have 2e to the t, and then this one minus that, which is minus 2e to the t. Then you multiply this with that, which is plus 1/2 d minus 1 d squared plus 6d plus 13 plus d plus 9 into y equals 0. Okay. So what is this? Okay, now we need to play around with this. Let's just play around a little bit. So 2e to the t. 2e to the t minus 2e to the t is 0. So this one we can just forget about. You can just forget about it. So okay, 2e to the 2e to the t like cancels out. And then we shall have this here. So we continue to have the following here. Okay, yeah. Okay, let's multiply out here, please. Second. Let's multiply out. So if you multiply out here, what are you going to have here? You're going to have like the 1/2 d times d squared is d cubed. D times 6d is 6d squared. D times 13, 13d Then you multiply these. And then plus d plus 9 into y. Okay. We get exactly this over here. To make things easy, because there's this half, that's like a disturbance, you can multiply everything by 2 here. And if you do that, that's going to be like a d cubed. You can even add the squares here. 6d squared, and that is going to be a 5d squared. D cubed, and then this is going to be a 5d squared. And then this one is going to be plus, okay, the 13 minus that is going to be a 7d, and then minus 13. And then now you multiply by 2. Like so. Okay, and then we continue. So on the next page, you're going to write this equation. D cubed plus 5d squared. And then now we're done. Okay, we can even add things up, like the 7d plus 2d is 9d. 9d. Okay. Okay, the 9d. And then now you have minus 13 plus 18 plus 5 into y. Into y, and this is equal to 0. Now this one, now we managed to get it in terms of y only. X is gone by substitution, by back substitution, if you like. So hence, the triangular system is therefore is therefore okay. Okay, so 1 second. Is therefore given by, okay, so we write this one first, d cubed plus 5d squared. Okay, and then the other one, it's this one here, 2x minus this. 2x minus the d squared. 2x minus the d squared minus into d squared plus 6d plus 13. Y equals 0. Ah, equals 4e to the t. 4e to the t. So this is the triangular system of the form in the question. What was the form? This one. Right, and this form is the form they gave to us. So, yeah. How different is this form from the actual thing that we obtained? Because they said it must be of this form. So how different is it from this one? So, right, it is of the form P1 y f1 of t p2 d x p3 d y f2 t. So you have this. Okay. So now, yeah, wanted to compare the form that's required. So they wanted this form, yeah, so you have only y, and then you have this. Right, so yeah, just a note there. Just a note there. So that is the kind of thing that obviously you need to sort of understand, and therefore we have, anyway, we're not done yet, we're still very far, because we're supposed to solve this question. Because now they said, now we just express it, the triangular system is therefore given by this, but you need to find the answer to this. Because they said, that's why it's 20 marks. Reduce it to an equivalent triangular system of the form this and determine the solution. So let's find the solution. Now, what is the solution to this? We're going to find the solution to this together, just now, in 1 second. Right, because once, okay, then we have the auxiliary equation. We now solve for y using, we now solve for y using the equation d cubed plus 5d squared plus 9d plus 5 y equals 0. Okay, from which you're able to get the auxiliary from the auxiliary equation. From the auxiliary equation. Which is m cubed plus 5m squared plus 9m plus 5 equals 0. Okay. Now this one you can factorize into m plus 1 using long division method or anything. Synthetic division, etc. High school methods is a cubic equation. If this is equal to 0. Right, so we have m plus 1. Right, so from which you are actually able to get m plus 1. Continue, m plus 1. And to just clean this up. From which you're able to get m plus 1. M squared plus 5 equals 0. So m equals that, and this one is a quadratic. So we're going to use minus b plus or minus the square root of b squared minus 4ac all over 2a minus 4 plus or minus the square root. The b is 4. A is 1. B is 5. Over 2a is 1. Which is minus 4 plus or minus. This is going to be 16 minus 20. 16 minus 20 is minus 4 out of 2. And this is minus 4 plus or minus. This is 2i out of 2. And this is minus 2 plus or minus I. What is the complementary function? So that the complementary function is given by y, complementary function of t e to the minus 2t. Cosine t b sine t. Okay, this is the complementary function from these answers. We got e to the minus 2t, then the I here, which is the imaginary part of the complex number, produces the 1t arguments, like cosine t, sine t. Then we need to find the particular integral. Okay, we are just continuing now. Okay, so it is the particular function, this one, but also we have another root, this one. So that is c e to the minus t for the minus 1. Okay. Substituting into 4.
Hello?
Okay. I'm just here now. After I got this, yes.
Where did you get this equation from?
Yeah, that equation is coming from the fact that we have this one. Because in mathematics, if the auxiliary equation has the roots m equals a plus ib, then from that point, what we're getting is the answer becomes e to the at into a times cosine bt plus b the sine of bt. So that sort of becomes the answer. So obviously this point is -2 plus or minus I. Okay, we take only the plus I, because the minus I becomes equivalent. So here it is E. So we use this formula, but obviously the real part of the complex number is -2. So e to the -2t into a cosine t, which means that you have a cosine t plus b sine t. Okay. So this is the answer. Okay, this is not the only root, because m is plus or minus this, but you only take the plus I. That's why it's only 1t, just t here, and the -2 real part is -2t. But you also have m equals -1. And the m equals -1 now is actually what we have here. Okay, but this, obviously, we need to find a general solution. So, but this is only the complementary function. The particular integral is next. The particular. Right, the particular integral. Okay, what is the particular integral? Well, the particular integral means we're going to consider the function we got and integrate. Right, so we're going to integrate. Let's just do that. So we're going to consider this one, which is d cubed plus 5d squared plus 9d plus 5, d cubed plus 5d squared. D cubed plus 5d squared. D cubed plus 5d squared plus 9d plus 5 plus 9d plus 5 into y equals 0. Okay, so for the particular integral, what you do? You get y and then you divide by this. So it becomes d cubed plus 5d squared plus 9d plus 5. Then you have 0, like this. So that now in the end, this is 0. No matter whatever you get out of these, it's just going to become 0. So this one is the particular integral. So the particular integral becomes 0. the particular integral becomes 0. Okay, so it becomes 0 plus a constant. We add a constant e. So you can just say it's e like that. Okay, also you think about this, you can take it that way, that it is e. It is certainly a constant, just a constant e. But now if you allow y to be 0, y to be e, you put it here. So this is going to make it 0, but this is going to mean that e itself is equal to 0. So you can just accept that this is 0, so that you can accept that the particular integral is 0. Okay? Now, what is the general solution? The complementary function, the particular integral added together will always give us a general solution. Use the more space than required. So that's okay. We're here. So therefore, I'm going to write in red now. Y general solution of t. Okay, y general solution is the complementary function plus a particular integral. Okay. Which means that y general solution therefore is e to the minus. Okay. First, let me just do this. It is the sum of the two. It is y complementary function plus particular integral, each of which is a function of t. Particular integral obviously becomes 0, function of t, so this one is e to the minus 2ta cosine t plus b sine t plus c e to the minus t, and this becomes like the general solution. Okay. Okay, take this now, you substitute into the x equation. You substitute into the x equation this one. We actually obtain, because this is the solution for y, and then we need to get the solution for x as well. So the one for x is this, the equation that is going to give us x, because the original equation is in terms of x and y. So which means that we have 2x minus into that, 2x minus into d squared, 2x minus into d squared plus 6d, d squared plus 6d plus 13, plus y, okay, plus y equals 4e to the t. Okay, just, yeah, equals 4e to the t. Okay, now you find the derivative. If you find the derivative Okay. X general of t, the general solution now for x is going to become, if you take this y and you substitute into there. Okay. What answer are we going to get? You're going to get 2e to the e, 2e to the t plus e to the minus 2t into 2a plus b cosine t plus 2b minus a sine t plus 4e, okay, 4c e to the minus t. So you have the solution for general solution for x and for y also. And we're done. We are done. We are done. And that's the answer for x and for y. And then now, because we have done this, we have solved this particular equation. And as we've solved this particular equation, we have obtained the answer. And that becomes the actual answer. And then now we're going to move to the next problem. Okay, now I'm actually going to load the next problem in the next minute. I'm loading the next problem in the next minute. Right. In the next minute, I'm loading the next problem. So now, let's look at the notion of what we call the root vectors. Let's look at the notion of what we call root vectors. And I know that this is a very simple notion, but we need to make sure we sort of understand this and we can be in a position to use this whenever necessary. I'm going to write down just briefly the actual definition. I know that it is bookwork and it is something that one knows, one should know because it comes in the exam. So it's very important. Let's write the definition. Right. Right. So what we're writing now is actually a definition. Right. So they're saying define the concept of a root vector of order k. K greater equal to 1 of a matrix A. So this is how we define this. A non-zero vector we can start by saying the non-zero vector. The non-zero vector, okay, I'm writing this because it comes in the exam repeatedly. So, right, the non-zero vector. The non-zero vector V is said to be a root vector of order K greater equal to 1 of the matrix A if a number lambda superscript star exists such that A minus lambda star I KV is equal to 0. A minus lambda star V is not 0. Okay, so in other words, the non-zero vector V is said to be a root vector of order K greater equal to 1 of the matrix A if a number lambda star exists such that this here matrix equation is true such that it's equal to the zero vector, but also if you subtract 1 from K, the times the vector V is not 0. Okay. So and then we get this. And I'm going to mention that if we bear in mind okay, this annihilation, I want to mention the annihilation part of this. So if we bear in mind that vector V is said to be annihilated, annihilated, annihilated by A minus lambda star I. Hey, if A minus lambda star I K V equals 0. Then we have a nicer version of the definition. Right, then the definition can be reformulated. Can be reformulated as Definition. The vector V is a root. So these are just the same, but yeah, it's annihilation. The second part I'm finishing. The vector V is a root vector. So we're going to be using root vectors in the next problem. It's a root vector of order k, where k is at least 1 of A. If a matrix or first if a number lambda star exists such that vector V is annihilated by A minus lambda star I. A. But not by A minus lambda star I. K minus 1. The vector V is the root vector of order k greater equal to 1 of A. If a number lambda star exists such that V is annihilated by A minus lambda star I all to the power k, but not by A minus lambda star A or I to the power k minus 1. Okay, note that there. All right, so we have noted that in this case, we have the definitions that are equivalent for the root vector. So in view of those two definitions, we therefore have defined the concept of a root vector for 2 marks. Right, and therefore we are pretty much done with the definition. And I want us to proceed to look at the next question. Right, just 1 second. We're moving to the next question. Right, so at this point, we are talking about let k be a positive integer. Use the principle of mathematical induction to prove that if A minus that is 0, then U is an eigenvector which corresponds to a non-repeated eigenvalue. Okay? Right. So let's look at these and look at how we can prove these with ease. Let's look at these and look at how we can prove this result with ease. I'm sure that it can be proven in many, many ways. You can either prove it now, or I can always make time to actually have this proven properly. And make time to make sure that this is proven properly. So I'm sure that I'm going to make time to make these, to make sure that we prove these properly. Let's move to the next question. Right, now there's this notion of the eigenvector method to solve that problem. So now if we use the eigenvalue method to solve this problem, right, obviously this solution is going to be pretty long. And it is very interesting for us to look at it. Okay, I've gathered these questions from the exam paper you sent to me. But it will be very interesting for us to analyze these and make sure that we are able to solve this problem in the most clearest of ways. In the most clearest of ways. Right. We're gonna do exactly that. So obviously there are a couple of methods that we can use to solve such problems. What are the methods that we can use to solve such problems? Right, we can use fundamental matrices, or we can use the eigenvector problem to solve this kind of equation. And I want us to use the eigenvector problem to solve this kind of a problem. I'm going to use exactly the eigenvector problem to solve this kind of equation. And we analyze these properly, thoroughly, analyze these thoroughly, because you need to get the correct answer to this question. Okay, let's get to it. Okay, right, using the eigenvector method to solve this problem, we first find the eigenvalue and then the eigenvector. Okay, let's just keep ourselves busy with it. Right, so we solve, the first thing we do is we solve the characteristic equation. Right, we solve the characteristic equation. Right, what is the characteristic equation and how do we achieve it? We've called it C of lambda. And C of lambda is going to be the same as what? It's going to be 1, this number 1, minus lambda. You take the number 2 minus lambda. Of course, you remember that, I'm sure, from linear algebra. We just subtract lambda from the main diagonal entries and the other entries remain the same. In which case, therefore, you have 1 minus lambda, 2 minus lambda minus 6. Okay, you multiply these, which is 1 by 2, which is exactly 2 minus 3 lambda. Okay, it's 2 minus lambda minus 2 lambda, which is minus 3 lambda plus lambda squared. I need to make sure I'm getting the correct answers because I've not done this question before, so I need to be very careful that we get correct answers to this. Okay, so 2 minus 6 is minus 4. Right, so need to make sure that it really works out to this. Otherwise, then you'll work out, you'll go on with the wrong thing. Okay, so that is that. Minus 2 lambda plus lambda squared minus 6, which is lambda squared minus 3 lambda minus 4. So yeah, it's correct. Okay, yeah, I'm gonna try to be faster. We don't have lots of time. Okay, this might be our last question. There are thousands of questions I prepared today here. Okay, so we have that. But now with this, if this equals 0, so that. Okay, first things first, so let's factorize this. So you have lambda lambda minus 4 plus 1. Okay, and from this, so able to get that lambda, so that lambda is 4, or lambda is minus 1. Okay, right. For lambda equals 4, okay, these are the eigenvalues. So we need to find the eigenvectors. Now to find the eigenvectors, we take this, we substitute into that one. So 1 minus lambda, 1 minus 4 is minus 3. 2 minus 4 is minus 2. U1, U2. Okay, let's move it to the next slide. Minus 3, 2. 3 minus 2. Minus 3, 2. 3 minus 2. U1, U2 equals 0. If I copy correctly, minus 3, 2, 2 minus 3. Minus 3, 2, 2, 3 minus 2. Yeah. Minus 3, 2, 3 minus 2. Okay. I'm having the right one. Yeah. Okay. So what we get out of this? We write the augmented matrix minus 3, 2, 3 minus 2. Then we do this. So which means minus 1 over 3 row 1. So, but here we can say row 2 plus row 1. Zeros, like this. Thus, we get U1. U1 is equal to the following. From this, U1 is equal to 2 over 3 U2. U2 is U2. So that U1, U2 what is U1? It is 2/3. U2 and this is U2. We can pull out the fraction normally, popular with the eigenvectors, so that we have a 2 only here and we have a 3 here. So that when you multiply again by these, 3 cancels here, 2, yeah, so it's fine. Well, we give the vectors names in this module.
Hello?
Yes, please.
What happened here?
Here, we said we multiplied row 1 by minus 1/3 row 1. So we divided by minus 3. If you divide by minus 3, divide minus 3 by minus 3, it's a 1. Divide 2 by minus 3 is minus 2/3, and divide 0 by minus 3 or multiply by minus 1/3, you get exactly the first row. Second row plus row 1, this second row plus that, so it's 3 minus that 0, this minus that 0, this minus that 0. You get the point. Okay. For lambda equals 4, the eigenvector, what is it? Okay, the eigenvector, you can call it, normally we give it the name big U, vector U. Call it vector U1. Which is 2 and 3. For the other one, lambda equals minus 1. Okay, so we're going to substitute into the equation. So is this one 1 minus lambda 2? 1 minus lambda 2, 3, and 2 minus lambda. 3 and 2 minus lambda. So we have 3 and 2 minus lambda. So this one, oops, something got pressed. So you have U1, U2, 0, 0. Okay. Minus 1 is 2, 2. 3, 3. U1, U2, 0, 0. Okay, for lambda equal to minus 1, you just put the minus 1 there. Okay, so we write the augmented matrix 2, 2, 3, 3. 0, 0. Row equivalent to, okay, multiply by 1/2 row 1, 1, 1, 0. Okay, you can leave this one for now. And then do row 2 minus 3 row 1, 0, 0, 0, 0. Which means that U1 is minus U2, U2 equals U2. U1, U2. What is U1 according to this? Is minus U2. U2 is U2. U2 is minus 1, 1. Okay. For lambda equals minus 1, eigenvector. Eigenvector is, okay, we give it the name capital. We give it the name capital, and then that was U1, so we call this one big U2. Big U2. And big U2 is this one. It's -1, then 1. Like that. Okay. Okay, we are here. We are there. So there's a common practice that sometimes is used in this module, that when you have this here, you can write this one as, for instance, the first one, you can write it as constant 1, 2/3, 2 and 3. So here you can write constant 1. And here, this one, for the thing you pull out, like here we pulled out U2. So this one is going to be constant 2, like this. And the constant 2 comes from the U2 place, and the constant 1 is like U2/3. This method is very popular. Very popular. Okay, let's look at the U1 now in terms of the notation we use of the C1. In linear algebra, we don't normally, we just take the constant to be 1. Okay, but now here we have that C1. So let's just maintain that. So that U1 is C1, 2, and 3. U1 is equal to C1 U/3. U1 is C1 2/3 and 2/3, 2 and 3, and U2 is C2 -1, 1. Like so. Okay, okay, we're finishing, please. We're using the eigenvalue and vector method to solve it. Now, okay, from these, so that these are the eigen vectors, so that x1 of t from the U1 becomes C1 2/3. E to the, okay, this one obviously corresponds to what? Corresponds to lambda equals 4. And this one corresponds to lambda equals -1. So that this x1 is C1, then e to the 4t. Then you have x2t, which is C2 minus 1, 1, e to the minus t. Okay. So this one here is a solution. It's a solution. It's a solution of x dot equals ax corresponding to lambda equals 0. Is a solution of corresponding to the first one is corresponding to lambda equals 4. And then the next one is corresponding to, yeah, this one is lambda equals 4, and this one is lambda equal to minus 1. So those are the solutions. Okay, from these part solutions, we have the general solution, the general solution is therefore given by x of t, which equals t1. We add them up, we add everything up. C1, 2, and 3 e to the 4t plus C2 minus 1, 1 e to the minus t. So this is a general solution. From the initial condition, from the initial value, okay, x0 is 0 minus 4. What we get? So we're going to continue using that one. So we're going to get x0 using the eigenvector method. So we have the eigenvectors and the eigenvalues have been obtained already. So this one is 0 minus 4. 2, 3. E to the 4 times 0 plus C2 minus 1, 1. Here we have this. 2C1 minus C2. Okay, so this one is 2C1 minus C2. And then this one is 3C1 plus C2. Okay. Now I need to just copy this on the next page. So we have 0 and minus 4. 0 and minus 4 is equal to 2C1 minus C2. 2C1 minus C2. Two C1 minus C2. Okay, here I need to write clearly. This one. So this one is like 3C1. So we have 3C1 plus C2. Which means 2C1 minus C2 is 0. These are like simultaneous equations. 3C1 plus C2 is minus 4. Can you solve this simultaneously if you take these two equations and you add them up? The result is this one is going to cancel out, giving us 5C1 is equal to minus 4. C1 becomes minus 4 out of 5, which means C2, according to this, C1, C2, C1 is minus 4 out of 5, which is minus 8 out of 5. Okay, we got those two constants. Hence, we have C1 is minus 4 out of 5, and C2 is minus 8 out of 5, like so. Okay. Now, what is the answer out of this? The solution of the initial value problem is therefore given by x, which is x1 of t, and x2 of t. And what is x1 of t? So we got everything, the C1 and C2. We can substitute everything into this here. If we substitute everything into that one there, C1 and then 2 and 3 for e to the t. Okay, let me first remove this. What is C1? Minus 4 out of 5. Okay, obviously we're using this C1 together with the previous, this one. 2 and 3. e to the 4t plus c2 plus c2 minus 1 and 1. C2 is minus 8 over 5, then minus 1 and 1. Then we have e to the minus t. Okay, we're going to check these answers with the initial value just to make sure that we made no mistakes here. Okay, so we just substitute the C1 and the C2. And now this becomes the answer, obviously. That is the answer, but I mean, this answer can be written like this, or also this answer can also be written as, you can multiply out. If you multiply out, this one is going to become what? 4 by 2 is minus 8 over 5e to the 4t minus 12 over 5e to the 4t plus 8 over 5e to the minus t minus 8 over 5e to the minus t. These are the same. So we're done. This is the answer. This is a solution. But I want to check this solution. So we're going to do a quick check. You recall that the initial value is a good way to check if this initial value is satisfied. So x0, what is x0? X0 is 0 and minus 4. X0 is 0 and minus 4. We have this. Can we try to substitute here? T equal to 0 here. So if you do the x0, then you're going to have minus 8 out of 5. Okay, if t is 0, then this is just 1. Plus 8 over 5. If t is 0, it's e to the minus 0, 1. Okay, you come to the bottom, same. Minus 8 over 5. So if you have minus 8 plus 8, it becomes 0. This becomes minus 20 out of 5. What is minus 20 out of 5? It's minus 4. So indeed, we're getting that x0 is that. So this answer is correct. And obviously, we have solved this problem. What was the problem? The problem was use eigenvalue, eigenvector method to solve the initial value problem. We found the eigenvalues 4 and minus 4, and the eigenvectors were found, and we solved the initial value problem. And this is the solution. If you check very carefully, we started at about 5:30. Right now is 20:48. Is PM, obviously. So right now is 8:48 PM. Yeah, so it's fine for today. Meaning that I will see you tomorrow.
What time tomorrow?
Yeah, the best time for me is like 4:30 because the day can be tricky, you know. It's the last day tomorrow. I understand because yeah. It's the last day tomorrow.